So today we're actually going to hopefully finish the first section of our syllabus. Right? So we have a little bit of topics to cover, but these topics can go as fast. Right? So the first thing that we're going to look at is work. Right? So we're going to look at what exactly is work and how do we calculate work. So we know that work is the force acting on an object to cause it to move a certain distance, right? So we know that work is calculated by multiplying the force times the distance moved, right? So work is equal to force times distance, and the distance that it moved would be the distance that the force is going, right? But also we can have this equation, force times distance times cos theta, right? So the cos theta part actually simplifies what work is and give us a better understanding of work. So let's look at that part. So let's say we're pushing on a box, right? So we're pushing on a box that's horizontal. So this is your force, right? And then it's going to move a distance d, right? Compared to the same box, but now we're pushing on the box at an angle with a force, but it's moving in that direction, right? So let's give these values a number. Let's say this is 2 newtons, 2 newtons, right? And let's say this moves 1 meter, and this also moves 1 meter. Now, the difference in terms of work is that we know that the cos theta, the theta there, tells us the angle between the force and the distance that the object moved. In our first example, let's call it A, we notice that the F and the D are parallel to each other. So both going parallel to each other, and in that case, theta would be 0 degrees. Right? So there is no angle created, so 0 degrees. So if we go with cos 0, we get 1. Right? So therefore, in this case, force is just, work is just force times distance, because cos theta, cos 0 is 1. But if we look at this case, right, where we notice that there is an angle created between the force and the distance. So we have the force going down and the distance going like that. So if we continue distance here, there is that angle between force and distance theta, right? So we should note that the highest that cos will go is 1. So that means if we have an angle theta, then that means it will be F times D times a number that's 0 point something, right? So whatever the angle is, it will be 0 point something else, right? And in that case, this work done will be greater than this work done, right? So we now look and see that if you want to do more work, right, with the same force, then you ensure that the force that's being applied is parallel to the distance that the object needs to move. So in cases that you want to move a box by pushing it, it will be done faster with more work, with less force. If you push the box forward in a parallel motion, so you stoop and push rather than pushing down on the box to push it forward, right? And this is what we've just noticed, right? So the work will be less if we stand and push down on the box to push it forward. In that case, we will need more force in order to do the same work as if we stoop and push it parallel to the direction that you want to go, All right, so is there any questions in regards to that? All right, great. All right, so in this case, we should note that the unit of work would be Newton meters, or more popularly used as Joule, capital J. So unit of work is Newton meter, which is measured, which is also the Joule, right? So this is basically all we need in terms of work, right? So this is how you calculate. It's a simple calculation in regards to work, and we'll look at some calculations when we finish some aspects of the topics, right? So since we've done work now, then we can look at energy. So what exactly is energy? All right, so I'm throwing that question out to you guys. What is energy? The capacity to do work. Great. All right, so energy is the capacity, or some persons will have the ability to do work. So once you have energy, then that means you have the capability of moving an object using a force, right? So that's what energy is, the ability to do work. Great. So we note that there are different types of energy, right? So let's look at some types of energy that we have. So let's start listing them. So different forms of energy that exist. So first one is kinetic energy. Great. All right, so let's look at kinetic energy first, and then we look at others. Potential energy. All right, so let's look at kinetic energy, which is abbreviated most times as KE. So we know that kinetic energy is the energy a body has because of its motion, right? So this energy is only present in objects that are moving. So if you're not moving, then it's not possible for you to have kinetic energy. So you have to be moving for you to have kinetic energy. And we know that the equation to find kinetic energy is half mass times velocity squared, right? So kinetic energy is basically energy objects have due to its motion. Equation is half mass times velocity squared, right? And then for potential energy, which is PE, is the energy a body has due to its height above the earth. All right, no, that's gravitational potential. Potential energy is the stored energy. So let's use that one. All right, so potential energy is stored energy, but we have different types of potential energy. All right, so let's start listing those types of potential energy that exist. The first one is, yes, any forms of potential energy. Gravitational. All right, great. So one type of potential is gravitational, which is the popular one that we know, which is the stored energy that an object has due to its height above the ground. Right, and we know to find this, it's the mass times gravitational acceleration times the height above the ground. Right, so sometimes it's normally delta H as well. It's the same. So if you're at this height and you need to find what's the change in potential energy if you move it to this height, then it would be from here to here. You find the height difference and you use that, right? But just in general, if it says that the object is 5 meters above the ground, then we use 5 to find the gravitational potential energy that's there. All right, another form is the elastic potential energy. So elastic potential energy is the stored energy that elastic objects have that will cause it, if you stretch it, cause it to actually come back to its normal position, or if you compress it, it causes it to come back to its original position. Right? And another one there is magnetic potential energy. right? And it's the stored energy that magnets have in order to attract or repel other magnets or magnetic materials, right? And so those are some popular forms of potential energy, right? But another thing to note is that these two energy forms, kinetic and potential, they actually form what is known as your total mechanical energy, right? So total mechanical energy is the value of your potential energy plus your kinetic energy, right? Because what this is basically tells us that every machinery, everything that operates on Earth converts energy between these two forms mainly. So if the object is moving, it has kinetic energy. If it carries it above the ground, then it has potential energy or just stored energy, right? So total mechanical energy is equal to kinetic energy plus potential energy, right? So let's just go through the others and we'll look back at this later. All right, so we have two forms of energy. Any other forms of energy that exist? Chemical energy. All right, so another form is chemical, and this is the your energy that's in basically in organic compounds. So organic compounds, so we eat mostly, so the energy we have in our body is given from a form of chemical energy. We eat food and we get chemical energy that we convert to different forms of energy in our bodies, right? Or it's the energy that compounds in chemistry they possess, right? Any other form? Sound energy, great. So sound energy, the energy to that objects that vibrate to produce sound, causing it to produce sound. Also electrical energy, light energy. All right, so light energy, the energy that objects have in order for it to actually create light. Electrical energy, the energy that electrons or protons carry around in a circuit. And all right, so those are the main types. And also you have nuclear energy. All right, so the nuclear energy comes from our atoms, the nucleus of atoms. So it's the energy that the nucleus of atoms has, that when it splits, it releases that energy form, right? So now someone made mention of our total mechanic or conservation of mechanical energy, right? And we're going to go to that now. So we know now that these are the forms of energy that exist, right? And we have the law of conservation of energy that states that energy cannot be created or destroyed, but changes from one form to another, all right? And that's what we're going to look at now. So we're going to use conservation of energy to actually see how does that work. So I'm going to use a roller coaster or just a bike traveling down as a hill. All right, so we have the hill and we have the ground. So this is the ground. All right, then the hill starts here to the person there. All right, it has a height above the ground of each. All right, so we're just going to use some random values. So we're going to say that the total mechanical energy in this system is 1,000 joule. All right, so that means there is no possible way that at any point here that the energy can exceed that value, right? So we're only going to focus on kinetic and potential energy. So we're not going to use any lost in energy as heat or sound, right? So we're only focusing on two types, which is potential and kinetic energy. So gravitational potential and kinetic. So PE and KE only. All right, so at the top of the hill, where the person is just about to ride off, right? What do you think the potential energy will be? Can we tell the exact value, or do we know an estimate of that value that it will be? Any answers? Just before the person starts to ride off, do we know what the potential energy in this system will be? 1,000. Great. So the potential energy of the person at the very top will be 1,000 joules. So therefore, the kinetic energy will be 0. Great. It is 0 joule. All right. So let's use halfway. So we are half the height at this point here. Can we tell what potential and kinetic will be? So halfway the journey, what would be the potential energy? 0. All right, someone gave 0. Is there any other answers? All right, 500 or 500. 500. All right, so 500 is indeed correct. All right, so if potential energy is 500, then our kinetic energy will be 500 as well. All right, and then finally now at the ground. So when the person reached the ground, so the PE and KE, what will be the PE when it's on the ground? The PE, so you're saying the PE is 1,000 joule, all right, but that's not 1,000. The kinetic energy is 1,000 joule. The potential energy will be 0 joule. All right, and let's see why. So remember the law states that energy cannot be created or destroyed, only changes from one form to another. And in this case, the forms I will be changing from would be from kinetic to potential, right? And in this case, the energy that we started off with is 1,000. So that means we cannot create any more from 1,000, or we cannot destroy any from 1,000. So at any point in this system, this total energy has to be present, right? So at the top here, before it starts to move, then kinetic is 0 because it's not moving. So therefore, potential energy has to be at its maximum, which is 1,000, right? So in this case, if we add both kinetic and potential, we get 1,000, which is our total amount of energy. Halfway the journey, right? So what's happening is that going down the hill, the 1,000 potential energy will start to decrease while the kinetic energy will start to increase. So halfway the journey of any system between potential and kinetic energy, halfway would always be half-half. All right, so therefore it will be 500 for potential, 500 for kinetic. And also if we add both, we get back the total system of 1,000 joule, right? And then at the bottom now, remember our potential energy is decreasing because the height is being decreased each time we're going down. So at the ground, the object reached the ground, so that means potential energy, which is mgh. There is no h here because now it's on the ground. So if there's no h, then that means potential energy is 0 joule, right? And if potential is 0 joule, then that means kinetic energy has to be 1,000. So when we add both, we get 1,000 joule, which equals back to our total system, right? So we notice that every point in our system, the total energy is always conserved, which is 1,000 joule. All right, so is that clear? All right, great. All right, so that's what potential, the conservation of energy is. So it tells us that, that at any point in the system, the total energy that was present first will always be the energy that's there, right? But we know in reality that conversion of energy does not happen just between potential and kinetic, right? Because the person will be riding a bike, the bike will have friction on the hill, so therefore there is heat as well, right? So therefore those types of energy will have its own value. But when you add all those energies, you get back the initial amount that was present. All right, so question, but for a body to have kinetic energy, doesn't it have to be in motion, right? But it is actually in motion at the bottom of the hill, right? Because remember, if you're coming down a hill, right, then you're not going to just stop right here. It's going to continue until you stop down here, right? So it's not actually stop here, but we're just looking at when the bike reached the end of the hill on the ground, what would be each energy, right? So it's not stopped. All right, all right. So those are the types of the forms of energy, the conservation of energy, right? And and we know that both equations for kinetic as well as for potential energy. All right. So we're just going to look at power now and efficiency, and then we do some calculations with each of these equations. All right, so let's go with power. So in power, power tells us two things. So it's either it's the rate at which work is done, or it's the rate at which a machine or anything converts energy from one form to another, right? So it's any of those definitions that you can use. So power is the rate at which work is done. So how fast do you complete the work, right? Or it's the rate at which you convert energy from this form to this form, right? And that so the power on your machines is actually most machines it's regards to the energy, right? So the energy of your bulb is how fast it can actually convert your electrical energy to your light energy, right? So that means we have power for two equations, that power is equal to work over time, or power is equal to the energy over time, right? And we know the unit of power is watt, which is a capital W, right? So that's what power entails. So how fast does it do work, or how fast does it convert energy from one form to another form, right? And in regards to power and work and energy, right? How fast it converts ties into the term of efficiency. So efficiency now tells us we're supplying the bulb with this amount of energy, right? How much useful energy can we get from the bulb, right? That's our efficiency, right? Or we're supplying this amount of power to an appliance. How much power can it produce from this power that we're supplying it to, right? So efficiency is given in regards to either power or energy. So it's the power output over power input multiplied by 100, because efficiency is a percentage, right? Or it can be the energy, useful energy over energy input times 100, right? So in reality, we never have efficiency of any machine being 100%. So this is never possible. Why is that the case? So why can a machine never have 100% efficiency? Meaning that the same amount of power that is sent to it is the same amount of power that it produces, or the energy sent to it is the same amount of energy it releases. It cannot support the pressure. All right, clarify that one for me. All right, so another one, because external forces like friction produces other forms of energy. All right, so I like that one. All right, so in regards to energy, any amount of energy being supplied to a machine, it will not be able to use all that energy to produce useful energy. All right, and that's because you're going to have byproducts like heat or light that is not necessary. All right, so let's take a washing machine for example. Right, it produces noise, so that's a form of energy that is wasted. Right, so, and when it's spinning, it produces heat, and we don't want heat in the washing machine, so that's also a wasteful energy. So that means those forms of energy that's always being produced that we don't want will cause it to not be 100% efficient, right? So that's why no machines on Earth will ever be 100% efficient, because every machine actually will have some form of movement, and because of that movement, heat will always be produced. All right, so if by any chance a product is being sold and it says it's 100% efficient, then you know that's not true. All right, so what we're going to do, we're going to restart now, and then when we return, we're going to look at some questions regarding work, power, energy, and efficiency. All right, so I'm going to restart now and then we look at some questions. All right, so we're going to start with some questions for work. All right, so it says, question 4. So the brakes of a truck causes it to slow down by applying a retarding force of 3.0 times 10 to the 3 newtons to the truck over a distance of 850 meters. What is the work done by this force on the truck? Is this work negative or positive, and why? All right, so let's look at that. So it asks us to find work, so we know that work is force times distance. All right, so in this case, the force given is 3.0 times 10 to the 3 multiply, and it says it's moved a distance of 850 meters. Now, because it says it's a retarding force is basically an opposing force on objects, right? And any opposing force, normally direction is in the opposite direction, which is negative, right? So when we multiply that, we get the negative 2.6 times 10 to the 6 joule. Right? So the negative here tells us that the force that's being provided is an opposing force towards acting on the object. Right? So because it's slowing down the object, it's moving. So the object is moving in that way, and it's slowing down while the retarding force is going in this direction. So that's the purpose of your negative here. Right? And that's the reason why you'd say if it's a negative work, because of that retarding force. All right, is that clear? All right. All right, so question 5. A person pulls a toboggan for a distance of 35.0 meters along the snow with a rope directed 25 degrees above the snow. The tension in the rope is 94.0 newtons. Part A, how much work is done on the toboggan by the tension force? And part B, how much work is done if the same tension is directed parallel to the snow? All right, seeing it better, no? All right, great. All right, so first part is how much work is done by that tension. All right, so because we're given now an angle, so we use force times distance times cos theta. All right, so the force given here for the tension is 94 times the distance, which is 35 meters, times cos of 25 degrees. All right, so because there is an angle created between the force and the direction in which it moved, we need to add this section to your formula, right? And when we do that, we get 2980 joule, right? So we get this amount of work that is done when it's at 25 degrees angle. But part B says if it's spiral to the snow. So that means if it's spiral, then that means cos theta would be 1. So, so we use, so the theta here would be 0 since it's spiral. So it would be 94 times 35 times cos 0. And cos 0 is 1, so it's basically 94 times 35, which we get 3290 joule. All right, and we notice that we did more work when it's parallel than when it's at 25 degrees angle. And that was from the first part of the lesson, right? So when it's parallel, you do more work with the same force than if you create an angle between the force and the distance. All right, so that's clear? All right, so question 6. I'm going to give you some time to do question 6. So 75-kilogram man is riding an escalator in the shopping mall. The escalator moves the man at a constant velocity from the ground level to the floor above, a vertical height 4.60 meters. What is the work done on the man by the gravitational force and by the escalator? 3381. Okay. 3450. All right. All right, so those seems to be the correct answer. All right, so let's explain the difference in your answers as well as why one is negative and one is positive. So the first part says the gravitational force caused by the gravitational force. All right, so remember the escalator is going up while gravity always trying to pull it down, right? So the work done by gravitational force is actually, it's a retarding force because it's going opposite to the direction in which your object is going. So your object is going up while gravity is going down, right? So in that case, the force that we'll use will be a negative value. So the negative shows that's a retarding force going opposite to the direction in which the object is tending to go. So for gravitational, it's force times distance. The force that we're going to use since we're given mass is m times g times d. So mg is your force, which is the weight. All right, so in this case, it's 75. All right, and we use a negative 9.8 to show that it's going down times the distance moved, which is 4.6. Right? And in that case, we get negative 3380 or 81 joule. Right? Now, if you use 10 as G, then you get the 3450 joule. Right? So any one of those answers will be correct. So that's when it's gravitational. When it's the by the escalator now, then that means this value is a positive because it's going with the motion of the object, right? So therefore, the acceleration will be positive, so you get a positive answer. All right, so the last one, question 7. So the 9.8 is G, gravitational acceleration. So you either can use the 10 or 9.8. Because remember, you're given mass, so we can find the weight of the object, which is the force. All right? All right, so question 7, and then we look at some energy questions. 42.833 degrees. All right. Yeah, so that's the answer there. All right, so let's look at that. So we know work is equal to force times distance times cos theta. They gave us the work, which is 1,100. The force is 30 times the distance, which is 50 times cos theta. Right, so 50 times 30, 1,500 cos theta, 1,100 divided by 1,500. All right, so that gives us 0.733 equals cos theta. So therefore, theta would be cos inverse of 0.733, and we get the 42.8 degrees. All right, so that would be the answer. So that's the angle between the force and the distance that will produce this amount of work. All right, so that's it for work. So let's look at energy now. All right, so we're just going to do one question for energy, which is question 5. All right, so it says a roller coaster cart, 500 kilograms, is to travel from 8 meters per second down a wavy hill of maximum height 80 meters. It will cause, without friction, near the end of the ride, it will make a death-defying jump. What is the total energy of the system at the top of the hill? All right, so it's all right, so something like that. So at the top of the hill, which the height is 80 meters, it's moving with a velocity of 8 meters per second. All right, and its mass is 500 kilograms. All right, so the total energy of the system, to find that, we just find the potential energy at the top of the the track, right? So the total energy at the top is the same energy right throughout, which is basically the potential energy. Because at the top, the cart will not be moving at that point. Oh, it actually is moving at the 8 right here. So this 8 should be at the top. So it's moving at the top as well. So it's both KE and PE. All right, so we know PE is mgh and KE is half mv squared. So the mass of the cart is 500 times g, which is, let's use 10, times h, which is 80 meters. So that's our potential energy, plus our kinetic half, the mass 500, times the velocity squared, 8 squared. All right, so when we do that, we get this part to be 400,000 plus 16,000. So that means your total energy is 416,000 joule. All right, so if you use 9.8 here, you will get 408,000 joule. All right, so this is the total energy in the system. Part B, what's the total energy of the system at the bottom of the hill? So at the top, the total energy is this. At the bottom, remember energy conservation. Energy is not created or destroyed. So that means at the bottom, it's the same total energy that will exist. Right? So the same 416,000 joule of energy will exist at the bottom of the track. What is the speed of the car at the height 30 meters? Right? So if we now highlight, so let's say this is our 30 meters, we want to know what the speed of the car right there is, right? But at that point, we know something special. We know that the total energy is 416,000 joule, right? So we know that, right? And we know at that point that this value, 416,000, is equal to potential energy, which is the mass, 500, times g times the height, which is 30, plus your kinetic energy, which is half 500 times v squared. All right, so we know that at 30 meters. All right, so in this case, we have 150,000 plus 250 v squared, and this is equal to the total amount of energy. All right, we take this over 266,000 equals 250 v squared. We divide by 250 on both sides, and we get 1064 equals v squared. So in order to find v, we find the square root. So v is equal to square root of 1064, which is 32.62 meters per second. All right, so is there any questions there? All right, no. All right, great. All right, so that's the speed at that height, and then it says that the speed at the bottom of the hill. All right, so the speed at the bottom of the hill is the same process. All right, but at the bottom of the hill, remember, it's saying at the bottom, so that means there is no potential energy. So in this case, we will ignore this part here. All right, so the total energy still remains, right? But the total energy is only equal to KE. So KE is half 500 V squared. So it's 250 V squared. So we divide by 250. So V squared is equal to 1664. And we find the square root of that, which is 40.79 meters per second. Right, so that's the very key to note, that at the bottom it's touching the ground, so therefore there is no potential energy. So all our total energy is actually equal to the kinetic energy, because the cart is still going to move when it reaches the bottom of the track. All right, so we're not going to do part E, all right, but this is how you would actually use for any single question, right? So that they normally use a roller coaster as an example in their questions, or so it's the same process right throughout, right? That sometimes they can ask you to find the height when it has a certain speed, right? Or you can ask to find the speed at a specific height in what we just did. All right, so it's the same process that you do. All right, so is that clear in regards to energy? All right, great. All right, so now let's look at some power question, and then we can look at the last topic in this section. All right, so we're starting from question 2. All right, so question 2 says a 300-kilogram piano is being lifted at a steady speed with a ground level straight up to an apartment 10.0 meters above the ground. The crane that is doing the lifting produces a steady power of 400 watts. How much time does it take to lift the piano? All right, so therefore we're given power, we're given the mass, we're given the height that it is moved, and we need to find time. All right, so which equation would we use for power? Remember, we had 2 equations for power, work over time or energy over time. Which one would we use to find power? Work over time. All right, so let's look at work over time. So we know power is equal to work over time. All right, so how would we find the work here? What would the work be equal to? So they're not given a value for work, so we need to find what work is. Force times distance. All right, and we haven't gotten any force, so how would we find the force? Because we're given mass, so m times g weight. So that means we have P is equal to mg d over t. All right, and if you notice this resembles our potential energy equation. So we could have just used potential energy over time. All right, so let's put in our values. So the power here is 400 is equal to the mass, which is 500, times g, which is 10, times the distance moved, which is 10, over time. All right, so this is cross multiply 400t is equal to 50,000 divided by 400. So therefore, t is equal to, wait, sorry, this is 300, sorry. This is 300, so this is 30,000. So we get 75 seconds. All right, so that would be the time it takes for the crane to lift the 300 kilogram piano to 10 meters. All right, so let's look at question 3. So it says in 2 minutes, a lift, ski lift raises 4 skiers at constant speed up to a height of 140 meters. The average mass of each skier is 65 kilograms. What's the average power provided by the tension in the cable lift pulling the lift? All right, so in this case, we're given time, and time is in meters, in minutes, sorry, so therefore we need to convert it to seconds, to our SI unit. So we convert minutes to seconds, so that means it's 2 times 60, which is 160 seconds. All right, so we have the time in seconds. All right, and it says that the mass is 65 kilograms, but it's 4 persons. Right, so multiply 65 by 4 because each person has an average mass of 65. So that's 260 kilograms. All right, and it also gives us the distance moved or the height, which is 140 meters. All right, and it asks us to find the power. All right, so we're finding power. We have mass, distance, and time. So again, we use the mgd over time. So the mass is 260, g is 10, distance moved is 140, over the time, which is 120. And we get the power to be 3033.33 watts. All right, so is that clear for everyone? All right, so let's see if we can do these two, question 5 and 6. Before this time we finish. All right, so question 5. What's the cost of operating a 3-watt electric clock for a year if the cost of electricity is $0.09 per kilowatt hour? All right, so that's another thing to note, that kilowatt hour is also a unit of energy, which normally your energy provider uses to calculate your electrical bill. Right, so it says that our power is 3 watts, right? It gives us a time of a year, which is 365 days in a year, and we need to know how much it will cost, right? So in this case, we first have to find the energy. So energy would be power times time, right? But we need to convert this because, and these two, right? So we need, because it says kilowatt, so we have to convert a watt to kilowatts by, how do we convert watt to kilowatts? Dividing, sure it's divide, yes it is divide. All right, so we divide by 1,000, so we get 0.003 kilowatts. All right, and then the days we have to change to an hour. All right, so we know that there are 24 hours in a day, so that means we multiply 365 by 24, and that gives us 8760 hours. All right, so now that we have the units that we need, we can multiply now. So the energy used is 26.28 kilowatt hours, right? And for each kilowatt, it costs, so for 1 kilowatt hour, it costs $0.09. So therefore, for this amount of kilowatts, our answer will be $0.09 multiplied by 226.28, and we get $2.37. All right, so is that clear? All right, great. All right, so the time is going to expire now. So I think that's good enough practice for these topics. All right, so when we restart, we're going to look at the last topic in this section of the syllabus, which is pressure. All right, so hopefully we can do some multiple choice questions as well for the ending part. All right, so closing off now and restarting. All right, so let's look at the last topic, and which is pressure. All right, so it's also not a complicated topic. All right, so pressure. So pressure is the effect of force on a specific area, right? So if you apply pressure, so when you stand, you apply pressure to the ground because you're applying a force onto the specific area that the force is being applied to, right? So the part that's applying the force, it has to touch the surface for it to actually contribute to its pressure. So we have two types of pressure that we focus on. We have pressure in solids objects, and we have pressure in liquid objects or in liquids, right? So pressure in a solid. So pressure in solid is equal to the force that's being provided over the area that the force is active, right? So remember the force, it has to be touching the area for it to contribute to it. So in questions or in just in imagination, if we have a box or any object, let's say a wooden block, and we put it on a table, but at the bottom of the wooden block, there is an opening, there is a space going right through the bottom of this, right? This space that is here will not contribute to the pressure being exerted on the object because there is no contact with that space on the table. All right, so that is key to note as well. All right, so we know that the unit of pressure is pascals, all right, which is a capital P and a common A. So Pascal is the unit of pressure, right? So another thing is, let's see, we notice that for a nail or a tack, it's actually manufactured in this manner. We have a slightly bigger head part that the hammer applies the force to, and it's actually a smaller tip for it to drive into the wall or wood, right? Why do you think the nail tip is actually a pointed tip rather than a bigger tip? So why is it a pointed tip rather than being bigger than how it is in regards to pressure? So it can drive in the surface easier. So why does it drive in the surface easier? What makes it otherwise from it being pointed? Why is it pointed in regards to pressure? How can you link the pointness of it to pressure in physics? Because this force will be required to apply enough pressure for it to go into the wall. All right, yes, we can work with that. All right, so the small tip means that this here is very small. So the area that will be applying the pressure is small, right? So if we have a small area, then that means we're going to get a high pressure, right? So small area means a high pressure, which means that we just need a small force to be applied for that nail to actually start penetrating the wood or the wall. So that's why the nails, not just because it's pointed, it's also made with that small tip because it reducing the area of contact. Right? So if you're supposed to turn the nail and try hammering the head of the nail in a wood, you notice that it will take more pressure, more force to be applied in order for it to start penetrating, right? So because the area is a very important part. So the small area means that we have great pressure, right? So it's the same thing with females wearing high heels, right? So the heels of those are normally is a very pointy or very small compared to a regular shoe. So you can walk on some glass on a regular shoe and it does not break. But as soon as you use a heel and you walk on it, right? You're noticing you're not increasing your force, right? The only thing you change is just the heel, right? You notice that once you start to walk, it actually starts to crack or break. And that's because the area, you're reducing the area, so that means your pressure is increasing. So let's see, if that's the case here, why can persons break an egg with just two fingers holding only the top and the bottom of the egg? All right, so two fingers on an egg, right? So you're reducing the area, yes, but the force being applied by those two fingers actually is being reduced compared to if you use your entire palm of your hand, right? So reducing your finger amount reduces the area, but it also reduces the force. So you're basically reducing both, so therefore the pressure actually is a very small number in comparison to if you use all your hand or even both hands and actually push on the edge of the egg. All right. All right. So this is basically what pressure in a solid entails. All right. Now let's look at pressure in liquids. Now in liquids, we all have been to beaches, pools, or some form of water that we go under at times. And we notice that the closer we are to the top of the water, right, we feel different pressure than if we're closer to the bottom, right? So we notice that when we're closer to the surface of the water, the pressure is less. But when we're closer to the bottom, we start to get a high pressure. The pressure is more, right? And that's because closer you are to the surface, the less amount of water is above you. So it's pushing, so the water is what's causing the pressure or the liquid, right? So you're closer to the top, so you have a little bit of water pushing down on you. When you go further down, you have more water being compressed on you. So that means you have a greater pressure. So that's why going further down, especially in the ocean, right, the pressure increases. So at the bottom of the ocean, right, that pressure is great enough that can actually cause damage, severe damage to persons that dive down there, right? So that's why they have to wear protective gear. So those gears can actually not actually withstand the pressure that will be exerted by the water. So in liquids, pressure is equal to the density of the liquid, right? So rho times g, gravitational acceleration, times h, The H here is the depth that it is, right? So the H is the depth that it is from the surface to the object, right? Now, you will see some books have plus atmospheric pressure, right? So some books will have plus atmospheric pressure. Now, we add atmospheric pressure only if the container is open. So if the container is open, then that means air particles will contribute to the pressure being provided by the water or the liquid, right? But if the container is closed, then that means air pressure will not affect the pressure in the liquid. So we only add atmospheric pressure when the container is open. All right, so is that clear? All right, great. All right, so also the pressure in a liquid, if we have an entire big container with a liquid, right? If we have at any point of the same height or depth, say this line represents the same depth. If we have an object here, an object here, small object here, a big object here, all these objects are on the same depth, even though their size change, they still will have the same pressure, right? So pressure in a liquid at the same depth, it doesn't matter the shape of the container, right? So if the container has more water on one side than the next, it's the same pressure that it exerts. So if your container over here is big, and then on this side it's smaller, right? And we're looking at this point, which is the same height as this point, these 2 points has the same pressure. The same pressure because they both have the same depth inside the liquid. So that is important, right? So same depth, regardless of the shape of the container, at that point, they will have the same pressure, right? Understanding? All right, great. All right, so the last thing for pressure is to actually use this principle to explain how the brake system in a car works. So we normally hear that about brake fluid, right, in cars. So the brake fluid is very important in cars because it contributes to the brake, the braking of the car. So when it stops, when we press on the brake, right? So a typical, and this system is known as the hydraulic system. So the brake system in car is the hydraulic system. So so it looks like this, right? So we have the fluid inside, and then of the fluid that produces the pressure, we have what is known as a piston, right? So the piston basically provides the pressure. Let's call this piston B and piston A. Now, piston A is what is actually connected to your pedal, so your brake pedal. So when you press your force on the brake pedal, right, we notice something about this side and this side. We notice this has a greater area than this side, and there is a reason for that. Remember that pressure, because this is a solid object, pressure is equal to force over area, right? We want to create a very big pressure on this liquid at the top right here. Because remember, at the same depth, this pressure here would be the same pressure that is sent to here, right? So we want to create a very high pressure here. So if we increase, the area, right, we increase the force as well, we can get a high pressure. No, sorry, it's the next way around. this side is connected to your pedal. Sorry about that. So the smaller one is connected to your pedal, right? So pressure is equal to force over area, right? So the small area, right, will cause you to have a high pressure because we just did that with the high heel shoe or the nail. So small area causes it to create a high pressure here, right? And that pressure is sent over in the liquid to be the same value that's going to apply a pressure to piston A, right? Now with piston A, it's connected to the disc, the brake disc on the wheels of the car, right? So the brake disc on the wheels of the car that will clamp on the wheel to actually slow down and stop the car. So remember now, we want a force. We're looking at the force that will be produced to cause the disc to actually stop the car. So force is equal to pressure times area, right? So we have a high pressure that's being generated here. So this pressure is high, and also the area is high. So therefore, our force that will be produced on the disc pad will be high as well, right? So that's how this system works to create a high force to actually cause the disc pads to actually clamp onto the wheels to stop it fast, right? So the smaller piston is connected to your pedal, which when you press on the brake, creates a force on that small area to give you a high pressure. Once you get a high pressure on this side, it generates a high pressure on this side as well because they're of the same depth, right? So this high pressure, right, and the big area will cause a great force to be produced onto your disc pads on your wheel. All right, so is that clear? All right, great. All right, so that's it for pressure. All right, so it's the same simple calculations that they normally use using these formulas. All right, so let's look at 2017 exam paper and see how much we can accomplish in terms of these topics that we've been through in section A. All right, so 2017 paper. All right, so an ice cube sinks in liquid A but floats in liquid B. Which of the following statement is true? The upthrust is less in liquid A than in liquid B. The upthrust is greater in liquid A than in B. The weight of the ice cube is less in liquid A than in liquid B. The weight of the ice cube is greater in liquid A than in liquid B. All right, so what's our answer there? A. So the upthrust is less in liquid A than in B. All right, so it sinks in A. So that means it's less in A because it sinks, and it floats in B. Yes, so that's correct. So A would be the answer. All right, so we have A. All right, B. Question 2. To measure the external diameter of a measuring cylinder most accurately, one should use a meter rule, tape measure, length of a string, or a pair of vernier caliper. Pair of vernier caliper, great. All right, 3. 4-kilogram mass is traveling with a constant speed of 5 meters per second. It is brought to rest in 2 seconds. The average force exerted on it to bring it to rest is. All right, so we're given mass, we're given the speed, and we're given the time. All right, so therefore we know, and we need to find the force. We know that force is equal to MA. Right, so we know that F is equal to MA. All right, someone said C. All right, let's see. So the mass is 4, right? The A would be V minus U over T, right? So the V is 0 because it's going to stop. U is 5, and the time it takes is 2 seconds. right? So it's 2.5 times 4, which is 10, right? So we get 10 newtons, which is C. Great. All right, question 4. Which of the following measurement has 3 significant figures? C, A. All right, so the answer is A. All right, so C is not the answer because all those numbers are non-zero numbers. Right? So therefore, 5 is the first one, 3 is second, 2 is third, and the 1 is the fourth. So that's 4 significant figures. All right, so significant figures is the first non-zero numbers. Right? So therefore, it can't be B as well because it starts with a 0. Right? So it's the first non-zero number. So in A, it's 2, and then 9, and then 3. Right? D is 4 significant figures because it starts off with a 1. All right? Question 5. Which of the following remains unchanged with an increase in temperature? Mass density, volume, relative density. A. Great. All right, so that one should be simple because mass never changes regardless of the change in any other quantities. All right, so 6. The length of the rod should be written as, all right, what should we write the length to be? Great. So the meter rule can only accommodate 1 decimal place of value. So it's 5.0, right? When an astronaut is standing on the moon, his mass is 70 kilograms. When he returns to Earth, his approximate weight will be D. Great, because remember weight is mass times G. Mass is still 70 and G is 10, so we get 700. All right, next. An object is returned from the ground and placed on a shelf. Which of the object's property is expected to increase? C, kinetic energy. D, yes, D. All right, so remember it's coming from the ground to a shelf, so we're increasing the height. So potential energy mgh, so that height increase, so kinetic energy increases. All right. All right, 9. Which of the following features must be present in a stable, well-designed racing car? Low center of gravity, narrow wheelbase, long front, or sunroof? A low center of gravity. Great. So when we have a low center of gravity, it's not easily toppled over. All right, next. The diagram below, drawn to scale, represents two forces S and T acting at O. Which of the following is a resultant in the direction OX? All right, so which one of these shows the resultant of the two forces S and T? All right, A, great. So both forces, the resultant has to be between those two forces. All right, so let's look at why it's not B. So it's not B because we notice S is longer than T. Right? So if S is longer than T, then your resultant has to be closer to the longer side. So, but X is closer to the T, so that's wrong. And it's not C, right? Because both S and T are the same length, so that means X should be halfway between S and T. And obviously it's not D because X is not between the two vectors. All right? 11. Which of the following expressions could be used to determine the speed of an object? And what's our answer? Speed of an object is C, great. Distance traveled over time taken. All right, next, which of the following is the unit of momentum? D, Newton meter. Are you sure? B. All right, so this is the fun part of physics. We don't have to memorize the units, right? Because we're supposed to know the equation of momentum, which is mass times velocity. So from that, we know mass is in kilograms, velocity is meters per second. So in this case, would be B, correct, which is kilogram meters per second. All right, 13. When two bodies bodies collide, momentum is conserved. This means that d, great. So momentum before is equal to momentum after. Great. All right, 14. Power can be defined as C, work done over time. Great. All right, 15, which is something that we're not there as yet. All right, so we have 9 minutes, so let's use that to question 2016. All right, so this is 2000 paper. All right, so 1 kilogram is equal to 1 gram, sorry, is equal to how much kilogram, how much milligrams? C. Yep, that is correct. All right, so 3.1415926 expressed to two significant figures is A, great, 3.1. All right, so 2 micrometers means, sorry. So micro is 10 to the negative 6. So your answer would be D, great. All right, next, which of the following has no units? B, great. So anything in physics that says relative has no unit. Which of the following instrument is best suited for measuring diameter of the strand of hair? B. No, it's not B this time. It's actually D. Right, so the strand of hair is too small for the vernier caliper to measure. So the micrometer screw gauge actually measures smaller diameters. So once it's a very small diameter, it's the micrometer screw gauge. If it's anything that can be easily held in the hand, then we use the vernier caliper. Right? So 6, which of the following is not an SI base unit? So it's meters, kilograms, ampere, centimeter cube. Centimeter cube, great. All right. Which of the following energy sources is or are renewable? Solar radiation, wind energy, fossil fuels. So renewable means that it is replenished. D, which is 1 and 2, great. All right, 8, if an object is moving along a surface with a constant acceleration, the net force acting on the object is B, constant, great. So once you have constant A, then that means your force also is constant. All right, 9. A mango hangs from a long stem in a strong horizontal breeze. Which of the following best describes the force acting on the mango? B, A. Yep, it is A. All right, so let's explain why it's A. So if we have the two forces, one going this way, one going that way, then your resultant force is going in that direction, right? Now, if the mango is actually remains on its stem, then that means there is an opposite force that's causing it to actually remain in that same position. So that opposite force is opposing your resultant force, which is going in that direction. All right, so this is your resultant force. There's an equal force, which is your tension force that causes it to remain on its stem. So that means A would be the answer. Yes? All right, so that's A there. All right, last question, or question 10. All right, so we have two light aluminum spheres, A and B, are suspended by insulating threads. If they come to rest, as shown in the diagram, the force keeping them apart is, all right, so what force will be keeping them apart? A, all right, someone said A. Any other answers? B. All right, so let's look at the possible. All right, so centripetal force, you don't know about that one, so it can't be that one because that's not CXC level. Magnetic force, all right, so there are just two metals, so there is no magnets present, so that means it cannot be. So it's either between gravitational or electrostatic. So remember, gravitational force entails objects pulling together to each other, right? So two masses pulling together. Because they are actually apart from each other, then therefore there is no pull towards each other. So therefore it has to be electrostatic, meaning that A and B has the same charge and they're repelling each other, right? So that means it is B, all right? So that's it today, guys. Thanks for watching and see you guys next time.